Okay, so for today we're just diving into another topic after cryptography from the previous video. Now we're just going to go over graph theory and a little bit of graph coloring theory, or the algorithm. So what exactly is graph theory and why do we need it? Well, some uses of it. It helps with modeling two-way networks and pairwise constraints. So by two-way networks, think people's preferences, maybe for foods or different just hobbies, or even friendships, like Facebook friendships. It goes two ways. Mutual friendships, we're assuming they're not unrequited. And then for pairwise constraints, we think of time conflicts that we potentially want to avoid, such as final exam scheduling and making sure that you don't have to be in two places at the same time for an exam. So the best way to outline graph theory is really with a picture, an example. So here we have a graph. We have several points, which are vertices, and several lines, which we call edges. So here we see that we have like a square shape and then something that kind of looks like a bow tie with graph 1. So this is a valid graph, okay? You have vertices, you have edges, and they are not self-looping. It's not just one circle with a vertex on itself, so it's not just looping to itself, And graph 2 over here is also valid, even though there's no edges, they're just vertices, they're just points. That also counts as a graph. So when we talk about vertices in these kind of graphs, we usually want to talk about something called the degree, which is essentially just how many edges a point is a part of. So for example, we say that vertex C has degree 4. So what does that mean? Well, if we look at vertex C, we can tell that it extends out to 4 lines. So it's part of this edge, this line. AC right here is part of CD. It's part of CE. It's part of CB. So it's part of these 4 little line segments. Therefore, we say its degree is 4. Similarly, for vertex E, we say that it has degree 3 because E extends out. You can see E is connected to 3 other line segments, 3 other edges. And then for G, we say that it has degree 2 because it only extends out as part of this edge with E and part of this edge with F. So that's how we define degree with these kind of graphs. So a few keywords we want to keep in mind that you might hear a lot: adjacency and incidence. They are similar, but it is very helpful to not mix them up. So adjacency just means 2 vertices that are connected by an incident edge. So let's go look at the definition for incidence and then jump back to adjacency. So for incidence just regards the relationship between one vertex and one edge where the vertex is one of the edge's endpoints. So if we go back up, for example, we see with this line segment, this edge AC, we see that vertex A is a part of AC. Therefore, we say that vertex A and edge AC have this incidence. They have this relationship that ties them together. A is part of AC. AC includes A. Okay? So another example could be with the line segment DC or CD, depending on how you want to say it. Right? We see that vertex D is part of DC. Therefore, we say that these two share an incidence. They have that relationship that ties them together. Now, when we talk about adjacency, we are talking about 2 vertices connected by an incident edge. So for example, AC. So in this regard, adjacency, we're saying, hey, this vertex is over here and it's neighbored by this vertex over here. Therefore, they are adjacent vertices to each other. And usually that relates if they are connected by an edge, such as with AC or with something like DC. Really, you can pick out any 2 vertices here that are connected by a line, connected by an edge, and you can say they share adjacency, they are vertices adjacent to each other, etc. Okay, so how do we describe degrees? Well, we already talked about how degree relates to essentially how many lines you see coming out of that one point, okay? How many edges are coming out of that one vertice, that one vertex we're focusing on. So the cool thing is with a graph, you can actually describe a graph using the degrees of each vertex in a set of parentheses like these. So if you went through, let's double check here, see vertex A extends out with 2 lines, so its degree is 2. B also extends out to 2 lines, so its degree is 2. C, we already covered that, it has degree 4. D goes out, you can see it's part of 3 median line segments, 3 median edges, therefore it has degree 3. And then F extends out as part of 2 line segments, 2 edges, so we consider it has degree 2, and same goes for G. So that's just how you describe the degrees of this specific graph. And another fun thing to keep in mind, that degree of V is essentially just the number of edges incident to V. That's basically another way of formally explaining what a degree is. You're seeing how many edges are incident, how many edges are involving this one point, right? So the general concept here is that a graph is equal to having a non-empty set of vertices, which you might also hear called nodes, but I will just call them vertices because it's a little more intuitive with the abbreviation. And then E is the set of bidirectional edges that aren't self-loops or duplicate parallels. So what I mean by the duplicate parallel part, suppose that you had another line segment next to FG, okay, and it wasn't connected to anything. You know, that in itself could be considered a separate graph, but for the sake of this, we're primarily considering line segments. We're considering edges that are not just duplicate parallels, and they're actually connected to something, right? These edges connect vertices, and they're not just looping on themselves. Like if you had F, and then it's just a circle that loops around to F, we will not consider that as a graph in this specific context per this concept definition right here. Okay, so that's a little more of the nitty-gritty. What is a vertex? What is an edge? Kind of sounds a little familiar, maybe with some terminology related to graphs before that you might have learned about somewhere, but this is the context and the set of definitions we assign for graph theory. So let's go into an example of an extension of graph theory. So when you talk about graph theory, you might also talk about something called a bipartite graph. So bi means 2. Essentially, a bipartite graph is a network split into 2 totally separate groups where the lines only cross between groups, not within them. It's a lot. We'll go over an example so it hits a little more concretely. Essentially, the average connection rates between these 2 groups are limited. They are locked to the ratio of those groups' sizes, so their population sizes individually. So this is an example out of the lecture I was listening to. Suppose that you have a curiosity about the Harvard versus MIT student friendship network. Let's just ballpark it. Keep the numbers simple for this example, because we do not want to do any crazy division right now. Let's say you have 6,000 Harvard students and 3,000 MIT students. Who has more cross-school friends on average? So real quick, we consider this a disjoint union because right now, for this example, we are not considering node overlap or internal links. So what does that mean? Well, when we're looking at Harvard versus MIT students, first of all, regarding node overlap, we are not going to consider someone who is both a Harvard student and an MIT student. In other words, they're enrolled at both colleges. We're not considering that for this example. Second, we are not considering internal links. In other words, with this example, we're not considering Harvard and Harvard friendships or MIT and MIT friendships, right? That's internal links, that's internal friendship links. We're only considering friendships between Harvard and MIT students. One Harvard student, one MIT student, they handshake, they become friends, etc. And there's a cool way to notate it too. So if you're familiar with the little U shape for a union, because we're talking about a disjoint union that has these kind of conditions, we put a little dot in the U, and you read it as, in this case, M is disjointedly unioned with H. In other words, if you were to find the intersection of M and H, there would be 0, right? Because again, we're not considering someone who is in both groups, and we're also not considering people that are friends within the same college. Okay, so how do we decide on this? Who has more cross-school friends on average? Let's see here. Okay, actually, not whose, who. Who has more cross-school friends on average? Well, let's think through some steps. Every friendship link contains one MIT student to one Harvard student. So the total number of edges, which you can calculate through the absolute value of E, the absolute value of your edges, those are equal, okay, right? Every friendship consists of one MIT student, one Harvard student. So every friendship link connects one to another. Therefore, your total number of edges are equal here. Second of all, the total number of endpoints, in this case friends, on the MIT side has to equal the number of endpoints, friends, on the Harvard side, because you're not giving an MIT student to a ghost. You're giving them as a friend essentially to another Harvard student, so there has to be a one-to-one for each pairing, okay? Therefore, the total MIT friends equals the total Harvard friends, and there we have it. So the average then is going to be the shared total divided by the respective population size. So what does this mean? Well, let's think about it. Average MIT friends is going to equal the number of friendship links divided by the size of your MIT group, right? And similarly, the average Harvard friends, the average number of Harvard friends is going to equal your total number of friendship links divided by the size of your Harvard group, okay? Each to their own. Average for MIT, you have the number of friendships divided by the size of your MIT group. Number of Harvard, you have the number of friendships divided by the size of your Harvard group. Well, let's see. What do these equations share in common? They both have the variable absolute value of E. So if we do a little rearranging, you can rewrite this as a multiplication problem in each case. For the MIT statement, for the MIT equation, you instead have the average MIT number times the MIT group is equal to the number of friendships. And similarly, same case for the Harvard group. Now, if we rearrange even more, we can set these equal to each other because they both equal absolute value of E, correct? So if you do a little rearranging, set these equal to each other, you divide both sides by the average of Harvard, and then you divide both sides by the size of the MIT group. Essentially, you get this form of the equation, which is the average MIT over the average of Harvard equals the size of your Harvard group over the size of your MIT group. It's simple rearranging, really. So if we plug in our numbers from earlier, we said that we have roughly 6,000 Harvard students and 3,000 MIT students. So we have vastly more Harvard students. So let's plug those numbers in. 6,000 divided by 3,000 is 2. So from that number, we are then able to make this conclusion that a typical MIT student has 2 times more Harvard friends than vice versa because there are simply fewer available MIT students. There's a lot more Harvard students. Therefore, on average, you would expect every MIT student has definitely more than one friend, okay? So this is an example of a bipartite graph where, again, see, we're looking at these 2 separate groups. It was students from different universities, and then we're seeing when lines cross between those groups, not within them. So like I said earlier, not considering Harvard to Harvard friendships or MIT to MIT friendships, but strictly the ones between one MIT student and one Harvard student. So that's one example. I'm going to pause for any questions. Do you have any questions? Honestly, compared to like some of the RSA and the cryptography, this stuff's a little easier, I think, to digest. So now, speaking of friendships, let's dive into something else called the Handshake Lemma. It's a theorem. So the idea of the Handshake Lemma, consider it like this. Whenever you shake hands with someone, that handshake involves two people, you and the person you're shaking hands with, right? Same idea for this lemma. So the idea of the handshake lemma is that every link has two ends. Remember the nodes, the vertices, what have you. So this little doodle here kind of visualizes it, right? Imagine, for the handshake, imagine each little node is a hand and those hands eventually meet, right? It takes two to make a handshake. So if you count all the connection points on every node in a network, the total is going to be an even number, okay? And this is a little fancy formal notation for it. What it essentially means is that the sum of the degree of V, which is like our vertices, for any specific vertex, I want to keep the case consistent here. For any specific vertex that exists in your set of nodes, your degree, overall, the sum, is going to equal 2 times the absolute value of E. So 2 times the number of edges in the network, links and all. So essentially, it's like saying, oh, we had this many handshakes, so how many hands were involved? How many people were involved, right? So intuitively, you should double it. That's why we have 2 times absolute value of the number of edges. Okay, so a few more examples to kind of visualize that. Imagine you have a network with 5 cables. In other words, the number of edges is 5. How many cable ends do you have? So the way I thought of it, I mean, I don't know if this is what was implied by cable, but I just thought of those little, extension cords where one end has a set of prongs that you plug into another end. So imagine that there's basically like an end on either, there's like a piece on either end of this cable. So the cable ends that you end up with is going to be double the number of cables that you have. So if you have like, say something like this cable, and we're counting this point, this end here, and then the other end, yes, I'm using the pen to visualize, yeah. But imagine this is your cable, and then you consider this end, and then this end on this side. So for one cable, you have 2 ends. So that's why you're going to double it. Because with 5 cables, you have 2 times 5, which is 10. And it makes sense because all the connection points summed together should be an even number, which 10 is even. Okay, now another example. This is people again. Okay, so let's say you have a Facebook network with only 4 users who have a total of 4 friendship links between them. So in this case, V is 4 for 4 users, and the number of edges we have is 4. So I drew out what this looks like. Basically, this is visualizing. Let's say Alice has 3 friends, right? She's friends with Bob, Charlie, and David. Bob is friends with 2 people, Alice and Charlie. Charlie is friends with 2 people as well, Bob and Alice. And David is only friends with Alice. So this is just a visual way to draw out that link connection there. So if we use the very fancy notation here, which is really just the summation of the total, degrees of vertices, we're going to take 2 times the lines, essentially, 2 times the number of friendship links, because remember it goes both ways, right? So for Alice and Bob, you have 2 people. Alice and Charlie, you have 2 people, right? Bob and Charlie, you have 2 people. So you're just going to count those links and double it because there's 2 people involved, even though we only deal with these 4 people. Yes, we're going to see Charlie again with his friendship with Bob and in his friendship with Alice. But every friendship involves 2 people. So that's what we're considering, holistically speaking. So for this, we take 2 times the number of friendship links, and that's why we get 8, because every friendship link needs 2 people to exist. Okay, another example, similar to the cable one, but I drew it out because it's a little easier for me to visualize too. If you have 3 pieces of rope, you fundamentally have a total of 6 ends. 1, 2, 3, 4, 5, 6. You are counting the top and the bottom end, okay? So that is what we mean essentially by the handshake lemma. And here's a fun little tip. So let's say that you want to figure out the maximum number of edges in a network with n vertices. Well, given n, we know that each vertex has to have a degree that is less than or equal to n minus 1. right? It can't be more than the vertices that you have. So what we're going to do then, if you plug that into the summation form, we just say then that the summation of, the degrees of v is less than or equal to n times n minus 1. And if we say that this summation is equal to 2 times the number of edges, like we said earlier, then you can just say 2 times the number of edges is less than or equal to n times n minus 1. So this is just a fancy little rearranging of some variables to get you essentially an inequality for how you can determine or how you can define the maximum number if you know the number of vertices. So if you have the number of edges in a network, well, essentially we're defining how you can find the number of edges in a network given the number of vertices, because that would be your n, and that would give you a maximum value, a upper limit, if you will, for the number of edges your network must then have. Okay, so, let's jump over here. So now we're going to dive into something a little interesting called graph coloring. So, what is graph coloring? It's kind of lengthy. It is defined as a proper k-coloring of a graph, g equals v comma e, and says that a proper k-coloring is a function f where v goes to c, where the absolute value of c is less than k, such that if u comma v exist in e, then f of u, I said f of u. I was careful about that. Some people just say the function letter and then the input, but I don't think you really should for this one. Then f of u cannot equal f of v. That was a mouthful, and if you're like me, when I read this for the first time, you're probably making this face right now, thinking, what the heck? But it's okay. We're going to dissect this line by line. So, a proper k-coloring of a graph, g equals v comma e. So remember, v is just our set of all vertices, the nodes, the tasks, the classes, etc. And the part is a function, f and then v going to c. So what does that mean? So f is a mapping function. So in coding, in programming, that would usually just be like a dictionary or a hash map where your key colon value is essentially the color map with the node equal to the color in that format. And then C is just the set of all available colors. So colors may not actually mean literal colors. It just may be things that we're trying not to overlap as needed. So time slots, execution windows, etc. Okay? And then when we say K over here, what is that little k? That k is your upper bound. So for example, if they say you need to find a 3 coloring, that means k equals 3, and you can only have up to 3 distinct colors in your dictionary, or maybe 3 distinct time slots if you're trying to schedule exams without making them overlap for students taking those classes together, right? And now the last line, such that if u comma v exists in E, then f of u is not equal to f of v. So what this means is that if you have 2 vertices, u and v, that have a line between them, the edge between u and v, in other words, they are adjacent, they are neighbors to each other, then that means the color you use for u cannot be the same as the color for v. So like if I have a red dot over here and then its neighbor is right here, I cannot use a red dot on that neighbor too because it overlaps, okay? It cannot be the same. That's how the coloring works. So let's see that with some examples. Trying to schedule final exams. How lovely is it when you have multiple final exams and they're all jam-packed right next to each other? Well, the crazy alternative would be, what if you had to be in 2-3 places at once if they were scheduled at the same time? That is an example that directly can apply this graph coloring principle right here. So let's say that you have these classes that need final exams scheduled for. You have biology, you have chemistry, physics, computer science, and psychology, okay? So keep in mind, for the points that have lines between them, so for example, chemistry and physics, okay? In this case, we are given some points here. We are given some details here. The edges between any 2 points means that you have at least one person taking both classes. So like over here, we have at least one person taking both bio and chem. We have at least one person taking bio and physics, at least one person taking CS and physics, at least one person taking chem and physics. You get the idea. Basically, if these 2 points are neighbors to each other, that means we have at least one student who is enrolled in both of them. Therefore, their final exams cannot be at the same time. That's impossible. So like for this student studying CS and Psych at the same time, they can't have their final exam at the same time. That won't work. So when we're talking about colors right now, we're just looking at time slots for the exams, okay? And that was a weird way for it to brush over. Let me see here. Nope. Wait. There. Okay. So given this graph, what do we need to know is how many colors do we need so that no final exams overlap? Because let's be honest, let's say you had hundreds of colors, hundreds of time slots that you could use, right? But you probably only want to find the smallest value that you need. You don't actually want to use 100 different time slots for final exam scheduling. You want to use the minimum that will work, okay? Obviously, one time slot's not going to work because you have too many people taking like pairs of 2 classes in this case. That's not going to work. So let's experiment a little bit. So this kind of touches on what I was just saying, but let's say yellow and yellow represents one time slot for final exams. Well, you can't do this because physics and chemistry have an edge between them, which means the student taking physics and chem will get those finals at the same time. We don't want that. Similarly, so you can't do this, and you also cannot do this. The student taking CS and psychology at the same time will also get their finals at the same time. That sucks. We can't do that. That's harsh. I mean, unless you have a time turner from Harry Potter, maybe, but we're assuming nobody has time turners right now. So we cannot do that. So now what about this? So we have 3 different colors here, 3 different time slots, okay? Does this work? Well, let's see. Bio and CS have the same exam time, but there's no edge between them, so it's okay. CS and Psych are next to each other, but they don't have the same color. They don't have the same time slot, so it's okay. It works. It's kind of like one of those, I'm not sure how much this relates, but it does remind me of one of those examples where they'll give you, say, a map of the United States, and they'll be like, oh, you got to color every state with like a few colors, maybe 4 colors, but no states, no 2 states that share a border can have the exact same color, right? It's got to be very various and diverse. So this works because for all the lines that connect points, we don't see like green here and then green right here, right? That wouldn't work. We have kind of more of a colorful alternation of colors. And this is not the only way to do this, by the way. For example, if we had, say, put biology here, maybe we put physics up here, you know, you'd probably get a different coloring. And there's no guarantee it would be the minimum number of coloring that you would get. But what you would end up with is definitely going to be something that works for this to go through. So in this case, no edges have endpoints with the same color. In other words, no exam overlap. So this works. We can use 3 different exam times to make sure no student taking pairs of classes get the same time for both classes. So what do we call this then? We have 3 colors. So we say that this graph can be 3 colored. In other words, well, actually for this problem, 3 is the minimum number of colors you need. So we say that its chromatic number is 3. The minimum number is the chromatic one. And we represent it as this, which is called chi of G, which is the graph. So that's lowercase chi. And even though we have 3 colors here, and we say it's 3 colored, there's actually a cool part about this. You could alternatively, again, use like maybe 4 colors. Maybe you have a palette of 4 colors to pick from, or 5 colors, but you only end up using 3. That's okay. You can still say this was 4 colored, this was 5 colored, because it doesn't mean you're using all of those colors. But ideally, you do want to find the minimum number that you need, so you don't have to go crazy with the color palette or with the time slot differences. And also, if we really wanted to throw it out there, we can also even say that this is a proper 13 coloring. Because what that means is you could have been given 13 colors and then decided to use 3 of them. That's okay. We're not judged on how many of all the colors we use. We just need to find how many we need for this to work, okay? But let's be honest, that's kind of time consuming, right? And actually, before we move on, I want to point out something funny about this. So this is just with final exam scheduling for what, 5 classes, some of which have edges between them. But get this, here's a fun fact. Now let's say you have hundreds of classes with thousands of people. In that case, finding the minimum number of time slots is going to be brutal. You're definitely probably going to want to throw more colors in and be like, okay, let's just use as many colors as we can to make this less painful, right? Because finding the minimum number of time slots with that many classes, that many people, that's going to be exhausting. So a brute force way to guarantee the perfect answer, meaning the minimum number you'd need, actually takes something on the scale of O of n factorial time, which in short is near impossible for a computer to calculate. So we have a way to call this kind of problem, if it ever scaled up to be that ginormous. We call it an NP-complete problem. So what does that mean? Well, I think I was asking you yesterday, and you were like, NP sounds like not possible, which honestly makes a little bit more intuitive sense. Apparently, NP stands for non-deterministic polynomial time. Such a mouthful, I get why they call it NP for short. So what does that mean? It just means this is a kind of problem that, yeah, when you have the answer, it's easy to double check, but if you have to answer it from scratch, good luck. It's hard, very hard. And the fact we say it's NP complete means that it's the hardest level of NP problems, near impossible to solve perfectly. This isn't something you need to memorize right now, by the way, but it's just a cool little fact that I thought of, like, relating to this problem. Okay, so let's say we did do trial and error, but let's say you really don't want to spend so much time doing trial and error with colors, or actually, more reasonably speaking, can we form a logical way to do this whole thing smoothly? Do we have like a logical approach to doing this if we don't know where to start other than, trial and error, this won't work, but this works? Well, that's where something called the greedy coloring algorithm comes into place. So it's very closely similar. It's very closely similar to the greedy algorithm. The principle of it works pretty much the same, I think. So for greedy coloring algorithm, we're basically taking a greedy algorithm for graph coloring. Okay, so what does greedy algorithm want to do for coloring? It just wants to make the best, most immediate choice for whatever node it looks at. So let's say we have a graph with 5 vertices and was it 6 edges. Yeah. So let's say, so for this algorithm, what it's going to do, we're going to have ranks essentially for different colors. Okay, let's say rank 1 is red, rank 2 is blue, and then we have green, and then yellow. So what this algorithm is going to do, it's going to start from the top. It's going to run through every color till it finds one that works, okay? So let's start with 1. We're going in numerical order. You could always rearrange these numbers, but we're going to start with 1, and our first color to use is red. Does it conflict with anything? No, we're good. Now let's move on to 2. Can we use red? No, because it's the same. It overlaps, right? It's just like with the exam scheduling conflict, right? If these little dots were exam times, you don't want them to be at the same time. You don't want points on the same line to have the same color, right? It's like the U.S. states problem where you have to color in every state and make sure no states next to each other have the same color. It's kind of like that. So this is not going to work. So what do? Well, let's see. Next color on our list is blue. So we try blue for number 2. Well, for point 2, not number 2. And that works. Okay? And now number 3, we can just start from the top. Again, we're starting from the top every time unless it doesn't work. And then we just keep moving down the list. So number 3, red is okay. 1 is red, but it's not right next to 3, so we can move on. And then 4, well, we can't use red because 3 is red. So we're going to use blue, and that works. Okay, what about 5? Can 5 be red? No, didn't work. But we can't use blue either. So then we go down the list to green, and now this works. Okay, so we used 3 colors to achieve this lack of overlap in this graph picture. So yeah, here's a tip. If you number the dots differently, so let's say we had 1 over here, 3 over here, 5 over here, you know, just different orders, right? Often you might get a different coloring, first of all, maybe with a different number of colors. So I've seen variations of this problem where you number the vertices differently, you end up using 4 colors, right? And you may not know that whether it's like the minimum number of colors you need, but you can at least be certain that using this algorithm, it will give you the best solution for what you're starting with, right? So in this case, the minimum we can use is 3 colors. Could we have used 4 colors? Absolutely. We could have swapped out this blue for maybe a purple or something else, right? But because we're just strictly trying to look for what is the bare minimum number of colors we need for this to work and there to be no overlap between adjacent vertices, this is how we do it. Okay, and here's one last tip, just a little bit more variable related. If the maximum degree of any vertex is D, then the greedy algorithm will color with at most D+1 colors. So for example, if the max degree of any vertex that you have is 3, then at most your algorithm is going to color with 4 colors. So just a fun little tip. And yeah, I think that pretty much sums it up for, let me see, did we go over everything? Oh yeah, I guess this is kind of just a last minute point, but when we're talking about degrees, one last thing, you might also want to think about degrees, examples that don't work. So what if I asked, does there exist a graph with degree sequence 2, 2, 1? Now remember, this represents the number, the degree count for each vertex. And the fact that we have 3 of them means that we have 3 points to consider. Well, let's see. If you have one point that has 2 degrees, it's got to shoot out through 2 lines. You got another one with 2 degrees, also shooting out from 2 lines. But for the 1, that doesn't work. This also has to be degree 2. So it cannot be degree 1. Therefore, this does not work. So therefore, there does not exist a graph with this degree sequence, because if you draw it out, it cannot have one that's degree 1. So it makes a little more sense if you draw it out visually like this. But I think intuitively, if you also look at it, you just need to count the points. And in short, remember, for graphs, you can have ones that are connected by edges like this, or you can even have ones floating in space like this. Yeah, so that wraps it up for now. I think next video we'll be going into matching and Hall's theorem and things like that. So that wraps it up for now, and this is graph theory, and that's it. And I really need a water.